In this lab, I will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. I used Tracker to extract the position of a mass in a video and modeled an identical system in VPython using Newton's second law and the energy principle. Finally, I will compare the accuracy of my model to the actual motion of the system. For the most part, my modeled system closely followed the Tracker video. Possible sources of error are from inaccurate Tracker point mass plotting and the increasing effect of the drag force over the duration of the 9-second video. For this experiment, I chose my system as the Earth, spring, and mass together. The two principles relevant to the system are Newton's second law and the energy principle. Newton's second law will predict new velocities and then resulting new positions. The energy principle states that the change in total energy of the system must be zero. Here's a video of my Tracker model. I calibrated Tracker with the given length and placed my axes where the spring is attached. After marking the point mass for the whole system, Tracker graphed the x and y values for me. I exported these values into a CSV file so that Python could read them for comparing the model to the actual video. For now, we are only concerned about the y-plot because this is the direction that the spring stretches, which we can relate to Hooke's law, F equals kx. I subtracted two congruent values on the graph, 2 crest points, and found the period this way. Given the period we found earlier, we can calculate the 3 necessary initial values. Number 1. Implement the formula for period, but solve for the spring constant, Ks. Number 2. Solve for the length of the stretch spring, SL, by setting Hooke's law equal to the gravitational force. Number 3. Find the relaxed length of the spring. Then, input these values into code, in addition to the mass of the item swinging and the initial position of the ball. These values can be found from Tracker. The code inputted is simple, and is shown at the bottom of the screen here. Here are the 3 forces at play. Gravity and the spring are all interacting with the mass. The third component, the net force, is the sum of these interactions. I subtracted gravity from the force of the spring in my net force calculation because it is in the opposite direction as the spring force. We will then calculate the velocity in a loop using the principles of Newton's second law and the net force that we acquire here. Here are the 3 energies of the system. Spring potential and gravitational potential energy combined with the kinetic energy of the mass should sum up to 0 as per the energy principle. The first code block we see here is the initial 3 energies, placed outside of the loop. The second block is comprised of the energy changes of the system. We need these values to make the nice pretty graph of the energies that we will see later. To update the spring during the loop, there are 2 components to update, the length and the tilt, seen here as L and spring.axis respectively. Subtracting the ball's position from the position of the spring, which is the origin, will give the length of the spring. Dividing it by its magnitude will get the direction vector, L hat. Subtracting the magnitude of the length from the original length will give the stretch, seen here as S. Finally, to graph the axis of the spring, use the position vector L. Here is my model in VPython. The red ball is from the Tracker video, and the blue ball is my model. As you can see, they follow a very similar path that we can say is the same. The lag between the balls is due to the slightly inaccurate point mass plotting and the drag force. The blue arrow is the spring force, and the black arrow is the gravitational force. As we can see, the black arrow always points straight down, but the blue arrow always points toward the origin, which is where the string is attached. Overall, my model does a good job predicting the motion of the ball. I also had Tracker output all the energies in the system on a graph. The blue curve is the kinetic energy, the red curve is the spring potential energy, and the green curve is gravitational potential energy. If you sum up all these energies, you obtain the value of 0, which is the yellow line. So for question 1, this then follows the law of the energy principle, that the sum of the energies in the system equals 0. Question 2 asks to compare the x and y periods. I already had the y period, so to obtain the x period, I used the same method of subtracting 2 congruent points on the x versus t graph. This time, the x period was 1.66 seconds. The x and y periods are different because the spring is swinging further in the x direction than the y direction. Given the elliptical shape of the motion, with the longer side of the ellipse being along the x-axis, the x-axis distance, which is calculated from the x period here, should be greater than the y distance. Therefore, the x length is 0.412 meters and the y length is 0.377 meters. This satisfies my